TED.
Good morning. I'd like to thank the organizers of this TEDx event and the U.S. Embassy in Lisbon for making it possible for me to be here this morning and to talk to you about what I expect will be some of the most important developments of the 21st century. The topic is nothing less than transforming the material basis of our civilization. And what I mean by that is all of the things that make up the built environment around us, all the things that you see around you in this auditorium, are products of today's material basis, today's means of manufacturing and production, the fruits of the Industrial Revolution. The prospect ahead is for a revolutionary kind of nanotechnology, something far beyond the material science that you may read about every day, something that has some parallels with the greatest nanotechnology that we have today, which is the nanotechnology that powers the the information revolution. Computers, telecommunications, today these are based on what is not called nanotechnology, but it's the technology of nanoelectronics, nanoscale devices working in billions together to arrange patterns of bits. The prospect ahead is one of mechanical nanoscale devices working together in billions and more to arrange patterns of atoms. And this has two aspects. One is atomic precision, and the other is high throughput. There's nothing small about what can be done starting with atoms and molecules. See, the bits being arranged by these nanoscale electronic devices need to have better software that more consistently produces the intended results. What makes this technology important isn't the gee whiz, the inner quality of it, but its potential for addressing urgent global problems. Transforming the material basis of civilization is what is necessary to do that. The collision of industrial civilization with the Earth's limits, is the great story of our time, from the point of view of crisis at least. And that crisis is based entirely on constraints on what we can make and how we make it, the energy required, the equipment, the products, and how those work. Human civilization, since its beginning, has been defined by the tools and materials that it uses. The Stone Age was, of course, defined by its stone tools. As the millions of years and then millennia passed, people learned to smelt iron and to make tools of iron, the tools of blacksmiths, hammering out products used in everyday life, but also hammering out the tools used by later generations of blacksmiths. The tools that led to the tools that led to the tools that led to the Industrial Revolution. A line of progress of greater precision, better materials, more intricate machinery, and machines that were used to produce better machines. Is there any possibility of fixing this so that I can advance the slides? I'm about 2 slides ahead here. There we go. This worked the first time, and it seems to be working now. So, the Industrial Revolution was based on learning better ways to use tools to cut metal. And that revolution carried us very far. People eventually learned to shape metal into the rocket engines that took our civilization to the moon. And doing so brought a new perspective to the world. The environmental movement was largely launched by these images of the Earth as a finite, closed system. And I came of age during the time of the environmental movement. I had a very small participation in the first Earth Day. And when I went to MIT, it was with the aim of trying to address this problem, this collision of industrial civilization with limits to growth. And so I studied space systems engineering as one way of looking beyond these limits and constraints. And there I joined a community of people who taught me something very important, which is how to dream bold, audacious visions and make them concrete and detailed and quantified, to look at what can be done by thousands of people with billions of dollars over perhaps decades, and produce concrete results that are subject to quantitative analysis where people can check the numbers. And so that perspective is one that I found myself turning to the molecular world, because during the 1970s, people in the molecular sciences were learning how biology works. And what they found at the bottom was a manufacturing process, the first of the molecular, atomically precise manufacturing processes that I'll mention, which is the material basis of life, which centers on genetic information, digital information being used to drive a manufacturing system, a productive piece of machinery. So what is happening in all of your cells right now is that genetic information is being transcribed into the same information in RNA, which is being fed through a machine called a ribosome, which puts together, see the strand coming out the top, the red strand, puts together amino acids, atomically precise building blocks, puts those together to make atomically precise chains, the chains of amino acids that then fold up to make protein molecules. Now, when I began to study this, I asked the question, what can we build with these tools? And soon concluded that it should be possible, would be possible, to learn to design and fabricate materials made of protein that hadn't been seen before. I published the first paper in this area, the one that founded the now burgeoning field of protein engineering. And when I speak of using these tools to move forward to build better tools, much as blacksmiths built better tools to move toward the Industrial Revolution, it's important to recognize what protein is. And when I say protein, people think of meat. Meat is mostly water. Instead, I would like you to think not of meat, but of horn. And horn is an engineering material. It has properties like wood, like polycarbonate, and it's important to keep in mind if you ever find yourself in a field with one of these animals that it's a weapons-grade biomaterial. Many people have discovered that to a major decrease in their health, shall we say. Now, in addition to being a hard material for weapons, it's an engineering material. As craftsmen, master craftsmen in Russia demonstrated in the 19th century, one can build something as intricate and precise as a pocket watch from wood, a similar biomaterial. And as with blacksmithing and progress toward the Industrial Revolution, the direction of progress, once again, will be toward greater control, better materials, the ability to make better devices and better machines, using tools to build better tools and to put parts together. Now, what one finds, what I discovered in investigating this area, is that the kinds of components that are used to make machines in the macroscopic world today almost always have potential counterparts in the nanoscale world. That devices like planetary gears, same function, can be built where the gear teeth are rows of atoms rather than pieces of steel. Differential gears, the same behavior, the same motion, the same function. And gear systems. Those are examples. They include drive shafts. They would be connected to nanoscale motors, bearings to allow the motion. And with these components, mechanical engineers know that they can build complex systems, including the kinds of systems that are used in manufacturing. And so this opens the door to manufacturing in the molecular world in a style that's very different from what we see in biology. So, in factories today, you find moving parts, taking components, bringing them together to assemble larger structures. And if you looked more closely at these machines, you would find gears and bearings and shafts and motors and conveyor belts. And all of those machines that execute these patterns of motion to bring parts together, form follows function. Motion paths to bring parts together are similar on the nanoscale and macro scale. The analogies are direct, very concrete. And so with these technologies, when we have the tools to build them, one can build manufacturing systems on this scale. And here's an illustration of the kind of thing that can be built. You can see here nanoscale machine parts bringing atomically precise components together, small molecules, transforming them, and placing here pairs of carbon atoms together to make, in this instance, diamond, which turns out to be an excellent engineering material. I should note a little background reading for scientists. This area of study is at the juncture between the molecular sciences and mechanical engineering. And mechanical engineers, by and large, do not understand the molecular sciences. And molecular scientists, by and large, don't understand mechanical engineering. And as a result, ideas have fallen through the cracks. There's been enormous confusion. Mythologies have developed, and there's a need for a much better grounded discussion. So I urge scientists in the audience to download Drexler's MIT dissertation, search and download, if you want to read about the quantum chemistry, the thermal fluctuations, the components, dynamics, and system architectures of these kinds of systems. So that addresses atomic precision. High throughput, scaling laws are crucial to that. You can see in nature how scaling laws work. Large birds flap their wings about twice per second. They're on a meter scale, factor of 10 down in size, 10 times the frequency, and so on. And extrapolated down to a 1 micron scale, you get rates of operation of 2 megahertz in this example. So it turns out that if you go through the exercise of designing these machines, you can measure the size. And the sizes are smaller by roughly a factor of 1 million. And so the scaling factor of frequency in this instance is a factor of 1 million. And what that means for manufacturing is enormous. When you get a factor of 1 million change in a parameter in engineering systems, you open a new world. It's fundamental. It's like the difference between a chemical explosion, a nuclear explosion, the difference between having a rocket that goes up into the air and falls back, and one that travels out of the solar system on a journey of decades. A factor of 1 million in speed means 1 million times more components per second per individual machine. Per ton of machine, it means 1 million times as much mass throughput. If a macroscopic machine can make 1,000 tons process 1,000 tons of material in a year, analogous nanoscale machines could process 1 billion. And that is where the potential for world-scale change comes from in this technology. So I've spoken of putting pieces together to make larger pieces. Here is something, again, like the components you see in factories. This animation was actually done by a mechanical engineer. What you saw there are small blocks being put together to make larger blocks. Now, spanning the gap between the nanoscale world and the macroscale world can be remarkably direct. Taking small building blocks, they can be put together in parallel by many machines working together to make larger and larger structures. And the scaling law for this kind of assembly is one in which, well, let's see, that example showed 4 assembly steps putting together 16 pieces. Take that forward, and one finds that 30 steps put together 1 billion. Of course, the purpose isn't to put together little tiles, but to put together intricate 3-dimensional objects, which might be made of superior materials, denser computational systems, putting blocks together to make larger blocks, which ultimately can be assembled into more familiar macroscopic systems. Now, if that block, the cubic centimeter scale, were a system built with atomic precision, it could hold 1 billion processor cores, 10 billion gigabytes of information storage, far beyond anything that Moore's law of progress promises. Building up with atomic precision from the bottom is a very powerful approach to improving technology. So I've addressed high throughput, comes from scaling laws. Atomic precision comes from starting with nature's atomically precise molecules and putting them together while not losing that precision. Atomic precision leads to new materials. Structure of matter can be controlled much more thoroughly. New materials leads to new components and to new systems. From this comes an unprecedented scope of production, the range of things that can be made, broader than what's found in industrial civilization, increases in scale of production, and reductions in cost. Billion-fold improvements in information technology, 10 to 100-fold improvements from better materials in aerospace, and even in mundane areas such as housing, lower cost, higher strength, higher efficiency, immunity to earthquakes, tornadoes, hurricanes, production on a scale that could bring a very high standard of living to people around the world. Now, what makes a change in our industrial technology base very urgent today, and this illustrates the notion that these systems resemble printers, digital information in, complex products out. What makes it very urgent today is that there's a need to transform our energy supplies quickly to move away from carbon to renewable sources like photovoltaics, and to deal with the increasing CO2 problem, which is changing climate rather rapidly. Levels increase despite international agreements and efforts to change technology and so on. They're expected to continue to rise. And to have the 21st century have a planet that resembles what we've had in the previous human history will require taking the CO2 levels down, and that is an enormous project. One can calculate the energy required. It's huge. The area of photovoltaics required to generate that energy is enormous. The costs are out of range of what can be handled by the world today. But the prospects with a better means of making things, more efficient, more capable, are to be able to do a project of that scale at low cost, taking molecular devices, removing molecules from the atmosphere, photovoltaics produced at low cost, to power those machines, can draw down CO2 and fix the greenhouse gas problem in a moderate length of time once we pass the threshold of having those technologies. And that is a matter of using tools to build better tools. We've gotten this far to the scale of the Industrial Revolution. We now have in hand tools for beginning to build with atomic precision, and we can see pathways from there to a truly transformative technology. So the future today increasingly looks, as many people feel, rather bleak. Running in the collision between our industrial civilization and the limits to Earth is becoming more urgent. Many people look forward and they don't really see a future. But now we can see a path that leads to a very profound change in how our civilization works, how it interacts with the world, one that can make a different 21st century. And so I think that in our homes, in our businesses, and internationally, it's time to begin to change our conversation about the future, to consider prospects that are very different, prospects that offer a new kind of hope for the future of our civilization. Thank you.